Yes, good morning everyone. Today we will do our second experiment of electrical machines lab 2, and today we are doing experiment on an alternator to find out the alternator regulation. Alternator regulation. This experiment we will be dealing with finding out the alternator regulation by using EMF and MMF method. So starting with the experiment, we will look into the machine details first of all. Just in the beginning, alternator, we are having a 3-phase alternator, 5 kVA, 50 Hz, 1500 RPM, 415 volt, 7 ampere. Here 415 volt is the line voltage and 7 ampere is the maximum load current that the alternator can supply. And the prime mover details are given on the right hand side as DC shunt motor. It is a 3.5 kW machine, 1500 RPM, 220 volt DC, 18.5 ampere. So these are the machine details. Now coming to the circuit diagram, first of all we will trace the circuit diagram. Before tracing the circuit diagram, we will show just what is there in the bed. We are having a DC motor, we are having a DC supply from here, that is a DC supply 220 volt DC. Now in the machine part you are having a DC shunt motor here, and then we are having an alternator. We are having an alternator on the right hand side. Okay, the prime mover is the DC shunt motor, and the mechanical input is given by the DC shunt motor to the alternator. Okay. Yes, now coming to the circuit tracing part, we will trace the circuit from the DC bed. The DC bed is a 220 volt DC supply. Okay, the circuit connection has been done by our lab staff, Lyson sir. So we will first of all move on to the DC shunt motor section. Okay. In the DC shunt motor, when you switch on the supply from the DC bed, the DC supply actually reaches this particular section in the control panel. With the help of this knife switch, the supply will be available at the point which is known as L. At the point which is known as L of the DC shunt motor. When you switch on the knife switch, you are having a supply here at L part. L part means in a 3-point starter you are having 3 sections: line, field and armature. These 3 sections, internally the supply will be available in the L. Okay, and here also it will be available. DC on section, here positive also, that DC supply will be available. You need not connect this and this together. They are internally connected. This thing and this point and this point are internally connected. Okay, now coming to the circuit diagram, you are having 3-point starter in the circuit diagram. You are having line, field and armature. Now we will first look into the field part of the DC shunt motor. The DC shunt motor, the field winding, you connect a wire from the point F and it will be directly going into the rheostat. The rheostat which is used here is 220 ohms 2 ampere, and this is the connection coming here. Then you are having the variable part, this one. Here you are having a variable part. You are connecting back this F, to F1. So in a DC shunt motor, the field winding is in between F1 and F2. So from the F point you connect the rheostat, from the rheostat it goes back to F1. And when you look at the circuit diagram that is shared in the lab manual, here F1, F2 is the field winding of the DC shunt motor. From F2 it goes to A2. A1, in between A1 and A2 you are having the armature. So F2 and A2 you have to connect. Okay, now looking into this section, A1 section. As you all know, the 3-point starter, line, field and armature, this A section, that is the armature, A point should be connected to A1. So in between A1 and A2 you are having armature winding, A2 and F2 should be shorted. So that is the part of the DC shunt motor section. And finally you are having a return path for that current. That return path of the current is connected from A2 to the negative part. That also you have to give. A2 and F2. See, look at here in the circuit diagram. A2, F2 and the negative part, they are all a single point. That is made possible by making use of this particular connection like this. You can see negative connected to A2, A2 connected to F2. That ends up the connection of the DC shunt motor section. Now coming to the alternator section. You are having 2 windings. First one is the field winding. Then you are having the stator winding or the armature winding. So let us first look on to the field winding. Okay, in the field winding section, you are having F1, F2 written here. This is part of the alternator. You can see here alternator written on the control panel, and you are having F1, F2, that is known as the field winding, DC field winding. Okay, so whenever you give the DC supply whenever you give the DC supply, the DC supply is available at the field winding section, or field winding section means the exciter section of the alternator. Now you can see here the exciter positive is there. Exciter positive is there. What you need to do is that in an alternator, the field winding section is also having a rheostat. That rheostat positive should be from the positive terminal of the exciter, it is going to the rheostat. Okay, and the variable part of the exciter is given to an ammeter. It is given to an ammeter which is connected in series. That means that the ammeter and the rheostat are connected in series. And the ammeter, from the ammeter, the negative part, it is going to the F1 section. It is going to the F1 section. And from the F2 and F2 you are having the field winding. From F2 it should go to the negative part of the exciter. So negative part of the exciter. You can see it is very clearly, you can see from the connection diagram. So we can have a series connection from F1. Okay, from F1 it will go to the ammeter. Ammeter and rheostat are in series with this field winding which is existing between F1 and F2. That is a field winding section of the alternator. Now coming to the stator part, or that you call it as the armature part of the alternator, armature. In that armature you are having 3 windings. It's a 3-phase alternator. So you are having R, Y and B. For our connection, what you are doing is that we need to connect Y and Y1. That is a connection that we have to do. That is according to this control panel. We have to connect this Y and Y1, B and B1. That is shown by 2 small wires. This one B to B1, Y to Y1. R should be connected to R1. But what we are doing is that we are having a series ammeter. We are having an ammeter that is connected in series with this. We are having an ammeter which is connected in series with that. You can see from here. This R wire is going to the ammeter part. This is an AC ammeter. So it is connected to the common terminal of the ammeter. From this common terminal, from the range of 10 ampere, it is connected to R1. That means that even though we have to connect R to R1, we are doing this with the help of an ammeter which is connected in series. Why? Because we have to measure the load current that is to be measured in the R phase. That is why the ammeter is connected in series. Now coming to the field winding section. In the field winding section, you are not in the field winding section, in the voltmeter section. In the voltmeter section, you need to measure the phase voltage. How will you measure the base voltage? By connecting a voltmeter in between the R phase and the neutral. Any one phase you can select. In this circuit diagram, we are selecting the R phase. That means that the voltmeter should be connected in parallel. That is, one terminal should end up in R and the other terminal should end up in the neutral. See the voltmeter here. You can see the voltmeter, which is a AC voltmeter. In this one, it is connected directly to the 500 terminal. So it is a direct reading. It's directly connected to 500. So you can have a direct reading from this range. You can use the calibrated scale that is written on the bottom is 500. So it's a direct reading here. Okay. Now coming to, we are having 2 experiments to be done. First one is OC test. That means open circuit characteristics. The next one is short circuit test. In the open circuit test, what you have to do is that all the three terminals of the armature or the stator of the alternator are open circuited. That means that if this knife switch is open, that means that all the 3 terminals are open circuited. If you need to perform a short circuit test, what you need to do is that you have to on this. And in the R2, Y2 and B2, all are short circuited like this. It is very much clear in your circuit diagram that has been shared in the lab manual. You can see that all the 3 terminals are short circuited in a short circuit test. Okay, in the connection you can very well in advance you can short this. Okay, what you have to do is that while doing open circuit test, you have to open this. That means that the 3 terminals, even though it is short circuited here, the no supply is coming to R2, Y2 and B2. That means that all are open circuited. If you want to short circuit, if you want to perform SC test or short circuit test, you have to switch load on. Load is on and you have to short circuit these 3 terminals. So by performing this particular experiment, okay, you can find out the alternator regulation by using EMF and MMF method. EMF method is also known as pessimistic method. MMF method is known as optimistic method. Okay, and all other things. You can see a knife switch here also. In the alternator, if you want to have the exciter on, that means the field winding section of the alternator, you have to on this. After that only, the supply will be available in this exciter. the supply will be available in the exciter. It's okay. Okay then. Yes. Today we will be performing the experiment now. We have already traced the circuit. We will be doing our experiment now. So in the initially we will discuss about the DC bed. The sir has switched on the DC bed now. The switch is in on position. So now the DC supply is available in that DC supply point positive and negative. With the help of this knife switch, the supply will be available at the L point of the 3-point starter. So sir is switching it on. Now initially with the help of how to start the motor. Motor is started with the help of the starter, 3-point starter. That will be demonstrated now. Yes, so the motor is running now. So first and primemost thing is that we have to set the speed of the motor at the rated speed, which is equal to 1500 rpm. So that can be set by adjusting the field rheostat of the DC motor. Field rheostat of the DC motor is that small rheostat that sir is varying now. Just we will look into the tachometer reading now. Now it is around 1396. That is not enough. We have to set it to 1500. Now the speed is 1424. So each and every time we have to vary the DC shunt motor field rheostat. Accordingly the speed will vary, and we have to set the speed as 1500. Now the motor speed is 1472. You have to bring it around 30 plus. You have to make it out around 1500. So now it is 1482. 1482, 1490. We'll have some relaxation time for the speed to set. I think this is enough. 1496 is enough. We'll have some variation. 1488. I think this takes some more time to set. Now it is fine. 1500. That is enough. Okay. So the motor is running at the rated speed. When the prime mover is giving the mechanical support or mechanical input to the generator. Now what we have to do is that the first experiment we have to perform is the OCC. In the OCC we have to plot a graph between IF versus EG. So what we have to do is that we have to vary the field current. We have to vary the field current. Before that we have to on the exciter. With the help of that knife switch, the field supply is provided to the alternator. Yes. Now the exciter is on. The field current is made available to the exciter section of the alternator. Now what you have to do is that we have to record the values of the meters. Initially we will have a DC ammeter here available. DC ammeter which is available, and it is marked as like this. Below the ammeter section or alphabet A, the mark is there which shows that it is a DC ammeter. This will measure the field current. Okay, and this will measure the voltmeter, that is a phase voltage. Since our first experiment is open circuit characteristics, the voltage that is measured will be always the phase voltage. Okay, so sir will be varying the rheostat. He will be taking different values of IF. Initially we will have to take the value for IF equal to 0. Some voltage will be there in the meter. That voltage is known as residual voltage. Okay, when IF equal to 0, the value of voltage that is measured is always equal to residual voltage.
EG 50, 50, 50, EG, IF 0.15, 15.
Yes. So slightly we will be varying this rheostat, and for step by step we will be taking that particular values of IF and EG. EG means the voltmeter rating, which is the no load voltage, or it is a voltage that is measured between one phase and a neutral. Step by step we have to vary. That variation should go up to 125% of the rated voltage.
EG 100.
I think it is 0.25. 0.25 IF. 0.25.
0.25. 0.25.
So you can see here. IF is equal to 0.15, initial reading EG equal to 50. Then you are varying the field rheostat of the exciter, and another value of IF is obtained as 0.25, and the EG is equal to 100. Like this, you have to take step by step reading till the EG reaches 125% of the rated voltage. Rated voltage is equal to 230. 415 is the line voltage, 230 is the phase voltage. So 125% of 230 will be equal to 275 volt. So 50, 100, 150, 175, 200, 250, 275. Till that, step by step you have to vary the rheostat. The variation is like this. You have to vary this rheostat. By varying this rheostat, what you do is that you vary the rheostat and you note down the IF values and the phase value voltages.
EG 125. 125. Another 125.
You can see that step by step the rheostat is varied and the voltage EG and IF is noted down. For 0.95 you are having a generated voltage of 250 volt. Now the final reading should be 125% of the rated voltage. You can record it as 275 voltage, the last reading. It's 1.1. Now what you have to do is that you have to reduce the IF to the initial value of 0 ampere. So for that particular reading you have to bring back the rheostat back to the initial position. That is what sir is doing now. Yes, now the OC test is over. Now the second thing that you have to do is that you have to do the short circuit test. For doing the short circuit test, what you have to do is that you have to switch on this load off from the off position to the on position. There is also a knife switch for that. When you switch on this knife switch, all these terminals R2, Y2 and V2 which you see in the bottom portion gets short circuited, where the three terminals are shorted. Exciter should also be on, and for short circuit test there is only a single reading. That single reading is that for a rated current of 7 ampere you have to measure the value of field current. So for that particular thing you will measure the value of this ammeter. This is an AC ammeter. And this is a field current here. For obtaining an armature current of 7 ampere, this 7 ampere is the rated current of the generator. What is the value of the field current? Only a single reading has to be recorded. For a particular value of IF, you get 7 ampere in the armature. That you have to record, and that will end up the short circuit test. So sir is varying the rheostat. He is varying the rheostat to bring the armature current here in this particular ammeter to 7 ampere. If it is set, he will stop there and record the reading. So gradually he is varying the rheostat. Very gradually he is varying the rheostat, bringing the ammeter to 7 ampere. I think it's almost set now. Now you can see that there is 7 amperes that is seen in this ammeter, and you have to record this ammeter also, which is a DC ammeter, which gives IF value.
IF 0.3.
So for an IF of 0.35 ampere, you are having an armature current of 7 ampere. So that is the end of the short circuit test. The other calculations and everything will be discussed in the online class. So again you have to reduce this rheostat back to the initial position. He is gradually reducing it. And now you will see how to off the machine. The machine is running. First of all you have to switch off the load part. Then you have to switch off the excitation part of the alternator. Now what you have to do is that you have to bring the motor rheostat to the initial position. That is the minimum position. So you are bringing the motor rheostat to minimum position. Now you have to switch off the knife. That is how you have to end up the experiment. Now the electromagnet will be demagnetized and the handle will be brought back now. Automatically it will come to the initial position like this. Okay. Yes. Thank you. Yes, now in the same experiment of finding out the alternator relation by EMF and MMF method, you need to find out the resistance per phase resistance of the armature winding of the alternator. For that, the circuit has been done, okay, and the supply is given from the DC bed, and when the supply is given from the DC bed, with the help of this knife switch, if it is on, the supply will be made available in the L portion. It will be made available in the L portion as well as the positive portion. We are taking this from the L portion. It is directly going to the rheostat. From the rheostat, it is directly going to, we are making use of a 100 ohm 4.1 ampere rheostat. From the rheostat, it is going to a DC ammeter. And this DC ammeter, the return wire is going to the R phase here. That means that the rheostat and the ammeters rheostat and the ammeter are connected in series. Okay. Now you are having a voltmeter that is connected between the neutral and the R phase. It measures the per phase. It measures the voltage that is available across R and N. This experiment is done to find out the resistance that exists between R and N. That measures the resistance between R and N. Since DC supply is provided, we are making use of VDC. We are making use of VDC and IDC. That means the 2 meters are DC meters. 2 meters are DC meters. So if you do V divided by I, you will get the value of RDC. But here, an alternator is an AC generator, so we are dealing with an AC supply, and we need to measure AC resistance. So RDC, if you calculate, we have to multiply it with 1.6 and you will get RAC. Okay, and that is how you have to measure RAC. RAC measurement is also involved in this experiment. Okay, and that is the way we have traced the circuit. So in this, you are giving DC supply. Okay, so sir is going to give the DC supply from the DC bed. Only one reading is enough. You need to measure only resistance V divided by I. No need to start the motor. You need not start the motor. Only thing is required is that you have to switch on the knife switch. So that the DC supply is available at the point L. And the rheostat is varied and a single reading is taken V divided by I. That is all.
V 2 volt.
V is equal to 2 volt.
I 3 volt.
I is equal to 3 ampere. I is equal to 3 ampere. So RDC will be equal to V divided by I. RDC will be equal to V divided by RDC is equal to V divided by I. So you will get RDC. You multiply RDC by 1.6, you will get RAC.